In this section, I'm going to introduce you to what are called polar coordinates. So polar coordinates are to be distinguished from what are commonly called rectangular or Cartesian coordinates. Now, Cartesian/rectangular coordinates are what you're familiar with. That's a way to specify a point by giving an x-coordinate and a y-coordinate, where we call, by convention, the horizontal axis the x-axis and the vertical the y-axis. Now, that word Cartesian, it gets its name from a mathematician who invented this whole system, whose name is René Descartes. So we take it for granted that sort of this has always existed in math, but it hasn't. Somebody had to actually invent this idea of specifying points in two-dimensional space using this method. And so we're all familiar with it. I mean, if I ask you to plot the point 3, 4, we know by convention that means you start at the origin. Start at the origin. And then you walk right 3. And you turn 90 degrees in the counterclockwise direction. You walk straight 4. And that specifies a point in two-dimensional space. Now, that is not the only way to specify a point in 2 dimensions. There's another way. And so, I mean, imagine it this way. Imagine that you're here. We're in a field, me and you, and we're at the origin. So there's you. I know you're at the origin, even though that's a terrible picture. But imagine you're standing at the origin. And I know that there's treasure buried right here. Right there at the point 4, 3. So, and you're blindfolded. So I can get you to that treasure. And the way I can do it is I could say, okay, face in the positive x direction, I guess we'd call that east. Walk 3 yards, turn left 90 degrees, and then walk straight 4 yards. And that will bring you to that treasure. However, another way I could get you there is I could just point you in the right direction, right? We're at the origin. I could just rotate you and point you in the right direction and have you walk straight there. Right? I could point you in the right direction and then you could just walk straight there. So that method of getting you to the point is what polar coordinates are all about. And so to make it more clear, let's use this example here. So in the diagram, I can figure out what the hypotenuse is in this diagram, because this is a distance of 3, that's a distance of 4, and so by the Pythagorean theorem, I chose this example because it would be easy and you're all familiar. Pythagorean theorem would produce that that's 5. That's a distance of 5. So I could point you in the right direction and this have you walk 5 yards out. However, we've yet to define what I mean by right direction, right? So there are certain ways to specify direction. One is just using angles. So I could have you facing the positive x direction, and I could just tell you to rotate the correct number of degrees, and then have you walk out 5 yards. So let's figure out in this diagram what the correct angle would be. Let's call that theta. So in the picture, tangent of theta, we know is 4 over 3, opposite over adjacent. And that means that theta is equal to tan inverse of 4 over 3, which when you put it in the calculator, you get 53.13 degrees. So this angle here is 53.13 degrees. And so that method of getting you there, me having you rotate 53.13 degrees counterclockwise, and then having you walk out 5 yards, that is what polar coordinates are called, or that's how they're described. So you start with the way they're labeled is you start with the distance you walk out. And then the next coordinate is the angle. So in our case, this is 53.13 0.13 degrees. And so the general form of a polar coordinate is, the first coordinate is r, so in our case r is 5, and then the second coordinate is the angle you walk out. And notice that's another legitimate way of getting you to a point in two-dimensional space. Here we're going to get some practice plotting points in polar form. So again, remember in polar form, your first coordinate is an r, the distance you walk out from the origin. And the origin, by the way, in polar form is called the pole. So just as for terminology, the origin is called the pole. So we know that's our r, and that's the angle we're walking out. So again, the way we view it is we're starting at the pole, and I do the rotating first. There's a few ways you can actually think about doing this, but I like to do the rotating first. So I imagine I'm there at the pole, and in this diagram what you should also notice is that each of these sections, right, each of these sections is divided up, these angles here, and each of them is worth 15 degrees if you look at it, right? Because there are, it looks like there's there's 6 of them in 90 degrees, and if you do 90 divided by 6, you get 15 degrees. So that makes it easier to graph points like, 30 degrees, 45, 60. That's the reason they've done it. A little harder when you have to do angles in between, but not so bad. So let's plot the point 2 pi over 3. So the first thing we're going to do is rotate counterclockwise pi over 3. Now we know that's 60 degrees. So that would be 4 of these sections. So I rotate 4 of those sections, and then I walk out 2. So each of these concentric circles here tells me how far to walk out. 1, 2. So again, there, notice that was a rotation of 60 degrees, and I walked out 2 yards. Now one thing I want to point out is, technically, see how these numbers are here? The 2, 4, 6, 8, 10, and then -2, -4, -6, -8. Technically that should not be there. So in any diagrams you'll see in the future, those won't be there, and they shouldn't be there because it's not always the case that, walking, I mean that's a Cartesian system, and we're in polar systems, so those really shouldn't be there. So I'll point that out at some point in the future again, but they're there I think now to kind of help us identify what walking 2 and walking 3 out looks like. Let's do the next one. The point R, 3, -45. So this time we're going to rotate -45 degrees. So we're facing, again, in this, what's the positive axis direction, and we're going to rotate down clockwise 45 degrees, and then walk out 3. So you rotate, and then walk out 3, and that brings you here. Okay, so that's R3, -45 degrees. And then the last one here, we've got -4, 3 pi over 4. Now we've yet to talk about what our negative radius means. So what that means is I'm going to, so I'm going to rotate the same angle here. So this angle, let's just put it in degrees to help us. That's 135 degrees. I'm going to rotate counterclockwise 135 degrees, and that faces me in this direction. So I'm going to just notate, it's going to face me in this direction, right? But rather than walk out 4 steps, I'm going to walk backwards 4 steps. So if I walk facing that direction backwards 4 steps, that would bring me here. Nope, it would bring me it would bring me right here. Okay, so we interpret a negative radius to mean essentially walking backwards after you rotate. So there are some examples of how to plot polar points, and we'll continue this idea in the next video.